So let's start the class. So I moved the exam date. The date for exam 2 has been moved to November 4. I think it's a Tuesday. So it will cover Newton's second law and Newton's law, action, reaction, and inertia. And whatever we're going to cover, right? Everything, Newton, what it's called, Unit 4. No. Unit 4 and Unit 5. Okay, it's the same format. So 20 questions, multiple choices, and in person, on paper, you bring your own equation sheet, no note, and so forth and so on. Okay, so November 4 is test number 2, and it's again 20% of the grade. Okay, so what else? And you do have in Dropbox, there is a tutorial. But in the tutorial, I'll go over the numerical problems. I don't go over the conceptual questions. So for the conceptual questions, make sure you take screenshots of the pop quizzes, right? When we have a pop quizzes, I cannot reopen them. So make sure you you screenshot them so you can go over them again. Okay, so I just want to go over this again because inclined plane is so important. So when you have a mass on an inclined plane, you will have at least 2 forces applied. You can have more, okay? You can have friction, you can have a pull or a push, but sure, you're gonna have the normal force and make sure that normal force is perpendicular to the plane, and you're going to have the weight. And make sure that weight goes straight down to the center of the earth. And then you always take the x-axis along the plane, so the weight will have 2 components. So you have to memorize it. Right? So what you need to memorize, so here you have the weight straight down. It has 2 components. The y component here, which is, here they call it the perpendicular component, perpendicular to the plane, and the parallel component. What you need to memorize is the following. And you see the angle, the slope here, the angle is theta. So that theta is going to be here. What you need to memorize is that component here is always mg sine. So the component of the weight along the plane is mg sine, and the component perpendicular to the plane is mg cosine. Okay, so in that case, okay, there is nothing up or down except the normal force and that component of the weight. So in this case, up equals down. There is no acceleration, so you can write mg cosine theta equals to the normal force. And normal means perpendicular. It's like a support force. Okay? Along the x-axis, it depends if you have friction or not. Okay, so if it's just the weight here, if there is no friction, okay, let's say it's frictionless, so then you're gonna have mg sine. So that will be the force unbalanced that will make you go faster down the slope. Okay, so if there is no friction, then you have mg sine equals ma. And you see that the acceleration due to gravity is going to be g, but it's going to be diluted because that's going to be smaller than 1. So the acceleration will be smaller than 10. Okay, if there is no friction. Now, if you have friction, it will be even smaller. You see that it does not depend on the mass. That was what Galileo understood. So for the pop quiz, right, if you have a race between a large mass or a small mass on a frictionless inclined plane, they will reach the ground at the same time because it's like they are in free fall, except that gravity is diluted. Okay, so the mass does not matter. So if you have an inclined plane that we don't have much in Florida, except when you go over the bridge, and you neglect friction because you have like wheels, right? You let go a big truck and a small car, they will reach the bottom here at the same time. So it does not depend on the mass. Okay, so you memorize it. The component of the weight along the inclined plane is mg sine. The component of the weight perpendicular here is mg cosine. It can go up, you can push, you can give it a push so it could go up and then go down. If it's going down, it's going to accelerate, right? So the acceleration is this way. So you're going to take the positive x-axis here. So when we get to more complex Newton's application problem, it's nice to have the positive x along the acceleration. It will make things easier. So I wanted to emphasize that. And then here I have a simulation. So here you have a very small, so you have static friction and kinetic friction. Yes. It's always what? So it doesn't matter which way it goes. Even if you can push it uphill, right? If you give a push, it's going to go up and then it's coming back. But the component of the weight is always mg sine along the inclined plane, and it's always trying to make the body goes down slope. So sometimes it's going to help if it wants to go down slope. If you give it a push and it's going up, so in that case, it's going to oppose the motion. Okay, so the component of the weight is always toward the bottom of the slope. That's what makes you going down slope. Is that clear? And then you have static friction. We're going to talk about friction, static friction, and kinetic friction. Static friction, it's when it's not moving. So it's possible that you have so much friction between the body and the plane that it's not moving. Like if you have rubber, for example, against cement, I don't know, so maybe it's not moving. And then once it's moving, you can have kinetic friction. But we're going to see that. Don't worry about that. So kinetic friction will be always smaller than static friction. You have a coefficient here that will only depend on the materials in contact. Okay, so but don't worry about that. I just want to show you this. You see here you have a little bit of kinetic friction, and the component of the weight make it go down slope faster and faster. Is that clear? Now, if you have kinetic friction balancing that component, then it will go down at a constant velocity. In that case, there is an acceleration because there is a winner. So we can say right minus left equals mass times acceleration. If they kill each other out, then it's moving at a constant speed. So I don't know, I can increase kinetic friction here. And then static friction has to be larger. Let's see if it wants to go down. Kinetic friction is 0.1. So you see, you have more kinetic friction. So to go back to your question, I can push it. I can give it like an initial velocity in this direction. I can do that. So now kinetic friction is the opposite direction, and then it changed direction. So the kinetic friction is always opposing the motion. So now we can do 5. Static friction has to be larger, so 0.5. You see, kinetic friction opposes the motion, and now static friction is so large that it doesn't move. Can make it to 0. To play with them, it's a little bit annoying. Okay, we can do that. Okay, but do you see that the component of the weight is always, it does not change. Okay, it's always down slope. Kinetic friction here is opposing the motion. You can play with that. These are amazing simulations. So I edited my slide and you have the link to the simulation. So I wanted to go over that. And then because there was a question in the pop quiz, and then about, for example, this example here, it's to illustrate Newton's third law. For every action, you have an opposite but equal reaction. So the shuttle is burning fuel, it's going to push on the exhaust gas. So the reaction will be the exhaust gas will push back on the shuttle. So the force is the same, but not the consequence. Consequence will be acceleration. It's because the space shuttle has a huge mass, okay? So that means its acceleration will be very small. The exhaust gas has a tiny mass, so its acceleration will be huge. So those space shuttle, they stopped it. First of all, there were two terrible accidents. There was the Challenger accident and the Columbia accident. The Challenger was even worse because it was the first time you had it was a teacher, kindergarten teacher, or I don't know if she was a kindergarten teacher, but a civil was inside the space shuttle, and there was this terrible accident. It was horrible. I think 1986, the Challenger accident, and then you had another accident, and then it was not very efficient, so they stopped doing it this way, and taking people inside was still dangerous, right? But anyway, my point is that they had to take, like if they had a load, so for example, when they took Hubble Space Telescope, take it into orbit, they had to take in fuel 20 times the mass of the load. So if you have the space telescope, you have to multiply by 20, and that will be the fuel that you need to get into orbit. So not efficient at all. So then they changed the technology, but it was great. Still very great. You heard about the Challenger disaster, right? It was very bad, and for engineers, it's important to understand what happened. Okay, and it was all over the news, and you see, she was a teacher, if I remember well. And then imagine all the kids, watching their teacher going into space. They were all excited, and all of a sudden, just after they took off, boom, there was a big explosion, and two pieces went in two opposite direction. That's conservation of momentum. But people saw some kind of very bad omen because the shape was the shape of a scorpion. Like if you look in the sky, it made like some kind of scorpion here. It went in two directions. And it's interesting because the scientist who understood what happened, and it was very bad engineering, was Richard Feynman. So he's a Nobel Prize, very, very smart. He was a genius, and he understood what happened. And so they told him at the time, the president told him, don't go public. We don't want to know people. We don't want people to know how bad we screw up. Right? But he did went public. So it's a very famous story. The story is that it has to do with the joints here that they used for the tank. Okay, they did test those joints for a given temperature. But in Florida, it was very cold that day, and they have not tasted the joint, like it's like rubber, right? For that type of temperature, and temperature was very cold. So what happened? It broke, right? You know when you put a rubber band inside the fridge and it can break? That's what happened. So there was a whole commission and there was a whole scandal at the time because a civil died in this disaster. So it's interesting for engineering. So after that, they decided to test for all kind of temperature or not to take off when it was very cold outside. So you can read about that. So anyway, this is a tangent. Let's go back to our business. So that will be part of the pop quiz. So go back. It says I have to go back. Any question? Okay. 92. So buckle your seatbelt. We're gonna take off. Okay, so this one we did together definitively on test number 2 because it's a multi-component system. So you should be able to divide it into 3 different systems. So you can have that system here, the 2 books together. So in that case, the only force applied is the push from the hand, because those 2 forces are inside the bag. You can think of it as an imaginary bag. So they kill each other out. Now, if you take only this book here, number 2, the only force applied will be F1 on 2. So it means it's being pushed by book number 1. If you take only this one in your imaginary bag, so you have 2 forces acting on it. You have the hand and the force from book number 2. So you really have to define your system. So we did that last time, and we did that last time. So I don't know where I am actually. We did that, 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 we did that. We did that, we did that, that here. So where I want to do, okay, here. So we did this one, but I want to make sure that everyone understand. Okay. Again, so let's say the acceleration is going to be this way because this one has a larger mass. So this one is going to go up. Okay. And then what else? Let's say they want you to find the acceleration. And I think here it says 50 kilograms. So I'm going to put a 50 here and a 10 there. We already did that. The thing to understand is that if there is an acceleration down, that means there is a larger force down. So this force here is the winner. Has to be larger than this force here, which is the tension. Okay, so it's the winner. So down minus up equals mass times acceleration. This one is going up, so the winner is up, but I need to have them both have the same length, because a tension, if you have a rope here and it doesn't have any mass and it's not extensible, it's not, you cannot stretch it, the magnitude will be the same. So that mass here has to be smaller. Okay, and then I show you how to do it the long way. Now, if you do it if you do it the short way, you take a bag. Okay, you have your bag here. Okay, so what's going on inside? You don't want to look, but you say the driving force here is mg minus the one that is opposing the move will be mg equals inertia. So you have inertia from this one plus that one. So it's going to be m plus ma. Okay, so that's the long way to do it, right? So you have 50 minus 10, is that right? Times g, which is 10, equals 50 plus 10 times the acceleration, which is 40 times 10 equals 60 times the acceleration. So A equals, what is it? 40 divided by 6, which is 6.7. Okay? Any question? Make sure you understand that. Once you understand that, it's make things easier. Of course, you can again do it in the long way. You can look at this one and you say down minus up equals mass times acceleration. You can look at this one and you say up minus down equals mass times acceleration. And you want to make sure you don't confuse the sign. That's why it's always easier if you choose the positive direction to be in the same direction as the acceleration. So that way you are not confused. Like, should I put a minus here or not put a minus? This way it's very clear. Is that clear? Okay, so we're going to apply the same thing to this kind of problem here. So you can think first, you can help each other. So again, you're going to have two ways to do it. This one is accelerating, this one is accelerating. So for this one, I want to make sure that's going to be plus here. This one is accelerating down, so down is going to be plus, because I want to make sure my acceleration will be positive. And then I have inertia. This one is 50. And this one here is 10. Again, you're going to have two ways to do it. First, we're going to say there is no friction. So nothing to oppose the motion here between the body and the surface. So if you look at this one, if you are focusing only, I don't know, shall I do red, green? If you're doing this one, which one is the driving force? Which one is the winner? The weight, right? It's the weight. That's the winner. That's what I call the winner. So it's going to be mg. And it's not in free fall because here you have a tension. Okay, the tension is fighting. It's the loser. But because you have an acceleration, that tension here has to be smaller than that one. And because the tension is always transferred, unchanged, that tension here is going to be here. It's going to be the same tension. Okay? And then you have two ways to do it. You can say, imagine that I'm going to put this like inside the bag. I'm going to put here. I can do it because the pulley, I don't know if I should put the pulley or not in the bag, but it doesn't matter. You see, I can do that because the pulley has no mass. If the pulley had mass, that will be another issue. And then I can say this bag is accelerating. So what is the driving force here? mg. T is inside my bag, so I don't worry about it, right? Equals inertia. You need to add them up, right? Because, of course, if you have a very, very large mass, it's not going to accelerate as much. Acceleration depends on the inertia times the acceleration. Okay? So the acceleration will be 10 over 60 times g. Is that right, or did I do a mistake? It's good. Times 10, right? So A will be times 10, which is 1.67 meter per second square. Are you with me? Now, instead of doing this way, you can decide to do it the long way. We're going to say, okay, we are just focusing on this one. So this one is accelerating down. So we're going to say driving force minus the loser, okay, the one opposite direction. So that will be T equals MA. And then I focus on that one. So in that case, the winner is T. That will be the one providing the acceleration. There is nothing to oppose. There is no friction. But you do have inertia. Okay, so it's winner minus loser equals inertia times acceleration. And if you have equation 1 and equation 2, you add them up, that goes away, and you have mg equals m plus ma. And you get the same thing. Agree? Right? Now, if you are asked what is the tension, so what is the tension? You would say T equals m times 1.67 Newton, and m is 50. Okay? Do you see? It's a trick. Now, if you want to do it the long way, the book will do it the long way, so you can do it the long way. Now, let's add some friction. So now we're going to add some friction. So you choose the way you want it. So I'm going to put some friction here. So friction is always between the two surfaces, right? So we're going to talk about friction when something wants to slide. Okay, the surface, they hook up with each other, right? It's like they hook like this. So you have to overcome that hooking, right, which is static friction, and then it starts to slide, but it's still hooking, like little hooks, right? It's like from the molecules. So it's between the two surfaces here. Kinetic friction is opposing. And now we have kinetic friction to be 40 Newton. So can you change the equation and solve? We can do it the two ways. Can do it two ways. Okay, so the first way, we're going to put everything in a bag. So mg is still the driving force. Inside that bag, you're going to have those tensions, but they are killing each other. And you have kinetic friction. So kinetic friction and mg are external forces, okay? They come from the outside. That comes from Mother Earth, and that comes from the surface. So minus the loser equals inertia. So that will be your inertia times the acceleration. So mg, that will be, this is 10, so 10, so that will be 100. Minus friction is 40, equals inertia, it's 60, times the acceleration. So it's going to be 60 equals 60a, so a equals 1. Agree? Now, if you want to do it body per body, so you can say, okay, I'm going to focus on this one. You still have mg minus t equals ma. If you focus on that one, you say loser, winner, okay, minus loser equals ma. And you will get the same thing, because when you add them up, if you add equation 1 and equation 2, you still mg minus kinetic friction equals m plus ma. You can use one of these equations to find t. Agree? So if you want to find t, you can say 50 times 1 plus 40. Any question? Yes? You have to buckle up today. Okay. Are you lost or is it easy? You with me? Right? Okay. So let's do this one. This is the most important. It's the most challenging, but it's very important for engineering, right? Projectile motion, it's cute, but it's not like you're gonna use it if you're doing mechanical engineering. Not that much. Okay, so this is also a two components system. And the idea is to really think through which system you're going to focus on. You can focus on system number one, you can focus on system number two, or you can focus on the whole system here. If you focus on the whole system, whatever is happening in the bag is not your business. You cannot open it up. If you focus on this system here, the whole thing, you're going to say, okay, I have a bag. My bag is 125 Newton, which is 12.5 kilogram, right? 100 plus 25 is 125 divided by 10. And it's being pulled up by some string. Maybe it's in equilibrium, or maybe it has a constant velocity, so no acceleration. Let's say there is no acceleration. So either is at rest or moving at a constant velocity, which means up equals down. This is up and this is down. That will be 125 Newton. So it just means that the pull here equals 125 Newton. Agree? Yes? Yes. Because the weight is mass times 10. Remember? Don't confuse. Mass is inertia, is how much stuff. The weight is the pull from Mother Earth. Let's make Mother Earth. See, Mother Earth is pulling here. So you have inertia and you have the weight, not to confuse each other. So this is a force and this is stuff. This is in Newton, this is in kilograms, right? Remember? So that will be a typical mistake because in multiple choices, they have to think what kind of mistake students can do. Oh, they might forget to divide by 10 to get the mass. So they will do that. That's why they do it. Okay, and then you have two systems. So let's say I'm focusing on system 2. So that system 2 is going to be in equilibrium between the tension. Okay, it's an external force. And then Mother Earth, 100 Newton pulling. So if I focus on number 2, you're going to have 100 down equals to the tension up. Agree? So in physics, you have to decide what is it that you are looking at. And now I can focus on number 1. So what is the force acting on number 1? The weight, very good. So I'm going to put a weight, 25 Newton. What else? The pull. Okay, so I have a pull. And what else? The tension, very good. Okay, it's not that intuitive. So you have up, P equals the tension plus the 25. Okay, so P, the pull has to be larger than T. Okay? Okay, let's take another example. Um, that's me pushing. I cannot do better push-up than this, okay? It's already something. Okay, I'm pushing here. So let's say this is the object here. And I'm pushing. Let's take the no, let's do it this way. Pushing here, and the push is 200 Newton. And then this is 10 kilogram. And on the ground, and let's say you have, okay, and you have some kinetic friction. So kinetic friction is always opposing. So that's going to be 50 Newton. Okay, and this angle here, so that will be the same angle there. You see it's in the 1 to 3rd quadrant, so that angle here is 40 degrees. Okay, find the acceleration. So it's a 40 pound, right? 20 Newton is 20 kilo. 20 kilo is 40 pounds. So this is about 40 pounds. Okay, so let's say it's accelerating this way. So I'm gonna take left to be positive because I like to have an acceleration along the positive direction. If you have issue with components, I hope you don't anymore. But remember that you can attach a cross at the tail of a vector. So you know how to find its component. I'm going to take this way to be positive. That's going to be my x-axis. That's going to be my y-axis. Agree? Yes? So along the x-axis, it's accelerating. Along the y-axis, nothing. Up equals down. So what is it that make it go faster in this direction? Is it the 200 Newton or is it the component? The x component, very good. It's going to be the x component, right? That will be your winner because A. Okay, so it will be 200 cosine 40 minus loser, which is 50, equals inertia, not to confuse with the weight, so it's going to be 10 times the acceleration. Okay? So don't stare. I don't know what you're staring at. Do it. 200 cosine 40 minus 50, enter, and you divide by 10. 10.3. Okay, so it's unbalanced. Now, along the y-axis, nothing interesting is happening. That because they kill each other out. So you have the weight. So now we have a weight, right? So you have a weight pushing down. So 100, you can see I'm pushing down. So it's being pushed down or pulled by Mother Earth. And because you push into the ground is going to fight back and you're going to have a huge normal force. Okay, that's a reaction force. So you're going to have up equals down. So along the y-axis, you're going to have up, you have the normal force that has to fight against the weight and against the y component of my push. Obviously, I'm going into the ground, so I'm going to increase like if you have a bathroom scale, it's going to read more. So it will be 200 sine 40. Okay?
On a practical level, like if you're pushing in, like would that not increase the friction?
Yes.
Why?
Yes. So very good. It's going to increase the friction. It's going to increase the friction because we're going to see that the kinetic friction equals the coefficient that depends of the material in contact times the normal force. So I could be able, I will be, so this is only, we're going to see that, but this is since you asked the question, you increase the friction by increasing the push in, and the push into the ground equals to the normal force. Now, it also depends of that coefficient because you see here that's some kind of carpet. I don't know, it doesn't slide easily. That's on purpose. Okay, it's not smooth. So that coefficient here depends on two material in contact with each other. And to find that coefficient, they have to do experiment. It's engineering doing experiment to find what's going to be the coefficient between them. Okay, so the coefficient in that case, you can do that experiment will be like if you can think of a demo, that type of demo, you can find the coefficient of the inclined plane. You can do that on your own. You have an inclined plane, you can see how to do it online, or we will see that. So it's going to be the coefficient here, which is 50 divided by this. Is that clear? Okay, so let's do, okay, your turn. Let's do this one. So it's being pulled and it accelerates. Okay, so you can take both bodies in the same bag. Okay, in the same bag, and you can say winner minus loser equals mass times acceleration. Where I am, I'm here. So I'm going to take this way to be positive, and I'm going to go that way to be positive. This force here has two components, right? You can make a cross. That will be the x component. I want that to be positive here. So it has two components. And this one has the weight. So this one has a weight opposing the motion. And this one has a x component here. And the y component, we don't care. But it has a y component. So x component. So and you have the tension. So tension here has to be smaller. No, 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 no. Just kidding. The tension has to be larger because it has to go up. So you have some tension here. And of course, you're going to have some tension there. Now I'm going to take everything in the bag, so I don't care about the tension. So that's going to go into my bag here, into my bag. I don't want to look what is inside the bag. That's one way. So what is the driving force here? What makes the thing accelerate to the right? Yes, the x component, right? We don't know what we have to find. So it will be the x component. I'm going to call it the x component, okay? F cosine. So x component minus, and then here you see it's accelerating up. This one is the loser. Okay, it's like opposing. I don't want to go. I don't want to go. M to G equals, and then you have inertia, which is m1 plus m2 times the acceleration. So again, you don't have to do it this way. You don't have to do it this way. Minus m2, so this is 50. So 5 times 10 is 50 equals m1 plus m2, that will be 15 times acceleration is 0.5. Okay, so the x component will be equals to 50 plus 7.5. So f cosine 40 equals 57.5. So f equals what? 30 degrees. Thank you. Something like 66 Newton. Did you get that? Yes? We divide by cosine 30. Yeah. Okay, now if you find it confusing, then you can do it the long way. You can say, okay, I'm going to focus on this one. So you have the winner minus the loser equals mass times acceleration. And then you focus on that one, which is the winner minus loser here, m to g equals the laziness, which is inertia times acceleration. And if you add equation 1 and equation 2, so 1 plus 2, you get the same thing. Some people have told me they don't like this way, they don't get it. So if you don't get it, it's fine, you can do it this way. And anyway, if the equation is to find the tension, you will have to write one of those equations. Yes.
You have to do G minus mu for M2 that's descending.
So now this one is going up because someone is pulling the string. It's pulling. So it's moving in this direction. If it's going that way, so then you have to do m to g minus t. So that's why it's important to have the positive direction in the same direction as the acceleration, because it will make things easier. Are we good? Okay. Okay, let's try to do the inclined plane. So you have an inclined plane, and sometimes you don't know. Is it going to go in this direction? Listen. Or is it going to go in that direction? There's a threshold, right? If obviously, if the mass is huge, it's going to go down slope. If the mass is huge, it's going to go up slope. But it depends on the slope, because the slope here is going to dilute the weight. So the trick is that you're going to give yourself direction. You're going to say, okay, let's say it's going to go down, so up slope. So the acceleration is positive. And if you find at the end a negative acceleration, it means you are wrong. and you have to start over. Get that? Sometimes you don't know. So that's why you always want to suppose a positive acceleration. And if you find a negative acceleration, then you have to start over because it's moving in the opposite direction. Okay, let's say there is no friction and let's say it's going this way. Suppose it's going this way. So I'm going to take plus in this direction. I'm going to take plus in that direction. So acceleration is positive. Okay, 6 kilograms. So this is 6 kilogram. This is 6 here. Okay, so try to do it. I think we already did something like this. So this is, here we need a winner. So that's going to be my winner. It's going to be 60 Newton. And they have a tension here, which is a loser. That tension here is going to be the same. And that's it because there is no friction. So it's sliding. Are you with me? No, no, it's wrong. I'm missing something. I'm missing something that I told you right at the beginning. What's happening when you have a weight or a mass on an inclined plane? Gravity, okay? And what will be that gravity? Always, always? Very good. Mg sine. Always, always, always the component of the weight along the inclined plane and down slope. And if it's moving this way, this is the loser. If it's going down slope, then it becomes the winner. But the direction is always, always, always the same. Okay, you always have the component of the weight looking down slope. And it's always mg sine. Which is, because you have sine 30, right? Yes, you're right, that will be 50. So let's take by doing my bag thing. Okay, I'm gonna put everything in a bag. I'm gonna say the winner, the driving force, okay, the one that is making the motion happen is 60, and it has to fight against this, which is 100 times sine 30 equals inertia will be everything you have in the bag. So that will be 16 times your acceleration. So that will be 60 minus 50 equals 16a. So 10 equals 16a. 10 kilogram plus 6. What?
We get 0.625.
Why do I get 0.62? Oh, you're right. So, okay. So 10 over 16 is 0.625, right? Okay. Now, if this is hard, you're going to take this system here and you're going to say 60 minus the loser equals inertia times acceleration. And then you consider this system, so t minus mg sine equals 10 times acceleration. You get the same thing. You can use that to find the tension. If I was to find a negative acceleration, that means I was wrong and the system is not going this way but opposite way. So in that case, I have to start over. I cannot try to fix. I cannot have quick fix. I have to start over. Okay? Okay, and then this one is more challenging because you see it's you have two boxes. Okay, so easy. You see, it's not moving. How come it's not moving? Exactly. So that will be called static friction. You push harder, static friction is still matching you, not going anywhere. You have to overcome static friction. And now you have kinetic friction. Kinetic friction does not change, stays the same. The applied force minus the friction will be equals to the net force, and that will give you your acceleration. You see the speed is increasing at a constant rate. And then you have only kinetic friction applied, so it's going to slow down. So my question is, if I put two boxes here, uh, so you still have a net force. How come the two? You see, he's applying the force on the bottom box, right? How come they don't slide? Huh? How come the top box doesn't slide off the bottom one? It's being hold up by the friction, right? If it was two pieces of ice, the bottom one will stay where it was because it has inertia, and only the top one will fall and the bottom one will move. Do you agree? So you have friction between both of them. Does it make sense? So that means that okay, you have friction between the two boxes, otherwise if the friction between them is not large enough, okay, so this one has inertia, it wants to stay here, and only this one will move, like the penny, right? When you do that experiment here and you have something that slides and you have a penny here, if you give a quick push here, the penny will fall because it has inertia. But here you have friction, so he's gonna push here. So there's a force applied to this box. Do you agree? That will be my push. And you have an acceleration. So how come this one is accelerating as well? Because it's not being touched by this one. Because of how come it's being taken with when it has no force? Because it's not that they are attached, but you have enough friction that box 1 and box 2, that will be the force of 1 on 2. And you have that push here. So this one, mass 2 and mass 1, it will accelerate at the same rate. Do you agree? So I can say that force 1 on 2 will be equal to the mass times acceleration. But what are the force acting on the bottom one? You have the push and yeah, very good. And you have the friction from the other one. Because for every action, you have an equal and opposite reaction. You cannot push without being pushed. The forces come into pair. If there is an action, you must have a reaction. So if I focus, so that will be only on the mass 2. If I focus on mass 1, I'm going to say the winner is the push minus the loser, 2 on 1, will be equal to M1A. So everything depends on the system you are focusing on. Okay? Now, if you consider the two boxes, do you have to take in account F21 and F12? No, because they're inside your bag, right? It's their privacy. It's not your business. You don't want to see what's going on inside. So if you take those two boxes, you're going to say the push, that will be the external force, equals M1 plus M2A. Isn't that beautiful? Physics is beautiful. And that's because if you add those here, you see F12 is the same thing as F21 in magnitude. And you can get so complex in those types of problems, right? In your book, especially if you want to go into mechanical engineering, you have to understand how to do those kinds of problems. It can be very, very complex. So don't open your book, do the solve problem. Now, if you are in biology, maybe you don't need to go too complex. Of course, you can if you want. Any question? Okay, we'll get back to those kinds of problem in the next unit. The next unit is all about that, but I build the fundamentals, right? So I'm not going to get back to this. Okay, and then we have static equilibrium. So you have two kinds of equilibrium. You have static and dynamic. Dynamic means that it's moving at a constant velocity. Static means it's not moving. In both cases, the net force is zero, so the acceleration is zero. Which means when you add the vectors, F1, F2, and F3, they kill each other out. Which means when you add them, it's a vector sum, F1 plus F2 plus F3 equals zero. And you did that for the lab. So let's say you have your grandma in a frame and you have a string. So that will be F1, another string F2, and that's going to be the weight. When you add those vectors, you get zero. So you can show that if you do it tail to head, you're going to get zero. Agree? So if you're you did that for the table, that the force table in the lab. It's they always do that. So if you have one vector here and I have another vector this way, so maybe it's two string. Okay, so you have two string here. So that will be the sum. Okay, so that will be the sum of the vector. Do you agree? Okay, tail to head or parallelogram. So if I want to make sure they're going to kill each other, I need to add another vector exactly this way. And now I see that F1 plus F2 plus F3 equals 0. I can do the tail to head. So if I do the tail to head, you go back to the same place. So it's like the displacement equals to 0 if you go back to the same place. You go this way, that way, you go back. The sum equals 0. So it's called the vector sum. Okay? So it's called equilibrium. Now, algebraically, so that was geometrically. Algebraically, it means the sum of the x component equals 0, the sum of the y component equals 0. Okay? In that case, it's easy, up equals down. Okay, so in that case, you see, if you have an object here and you have a string, the student A is pulling this way, the student C is pulling that way, student B is pulling this way, it's not going to go anywhere because those forces kill each other out. Up equals down, right equals left. So this is little Susie. Little Susie comes from that book, very famous, Paul Hewitt. He was very, very good at drawing. He has this very famous book, Conceptual Physics. It's a great book. So anyway, what do you think the tension is in H? Huh? So down is 300. I agree, you need 300 up, but you have two strings. It's going to be what? 150 and 150, right? So it's going to be 150 here and 150. And you could be confused because here there is a pulley. This is attached to the ceiling, this pulley, and then there was the wall. It doesn't matter. All I want to focus, I put little Susie, excuse me, Susie, in a bag, and that bag is being pulled by this string, by that string is touching, and then Mother Earth is pulling down. So I don't care what's going on outside. Okay? So I can say everything up equals everything down. So up is T1 plus T2 equals 300. And because the angle, I mean, they have the same direction, so they share. So 2t equals 300, so t equals 150. Good?
Wait, so
Yes.
we pick our signs to be as if like we pick it to be positive or negative.
So in that case, it doesn't matter. You instead of thinking sign positive or negative, you can just say up equals down, right equals left, because there is no acceleration. If it's acceleration, if there is an acceleration, then you want to take the direction to be positive in the same direction as the acceleration. But in that case, it depends which way you do it. That's my way to do it. I say up equals down. Now, if you don't like my way, so then, yes, you can say up is plus and this is minus. So you're going to have the sum of the y component equals 0. So this component is positive. This component is positive. And the y component will be negative. So minus 300 equals 0. It's a good question, actually. So this is the book way. So you can do it this way. So in that case, yes, there will be a sign involved. Or we can just say up equals down. So if you do it this way, you don't have any sign. It's just the magnitudes. Okay, so either you do up equals down, and then you don't have any sign, you don't have positive or negative, everything is positive, or you do it the book way and you say the sum of the y component equals 0, and y component can be negative. Likewise, you can say right equals left, so in that case there is no negative, it's just the magnitude. Or you can do it the book way and say the sum of the x component equals 0. So yes, then you have to decide which way is plus, which way is minus, because some of the components can be negative. So it's a good question. Yes? Today is not easy, okay? It's not an easy day. It's not a fun day. I put in a Canvas a video, interesting video about, you watch it? It's interesting, right? About space. So sometimes you have, and do you see how he lost weight? Like that will be a great way to lose weight. So you send people like this in space, and then they lose weight. And then you get Sue. Okay, let's do it with our guts. Let's do physics with our guts. So you have F1. So let's say you have a box on the floor, and let's not worry about friction. You have F1, F2. Obviously, if you want that to be in static equilibrium, you want to have F3. Agree? So imagine that if you add them up, okay, you need to have a force exactly the other way. Exactly. So they're gonna kill each other out. So we're gonna have F1 plus F2 plus F3 equals 0. Now, if you look at the component, so I don't know, let's say if it's on the ground, maybe this is east, west, north, and south. You want to make sure that east equals south, right? So that will be your x component for that vector, and that will be the y component. Do you agree? So that's what makes sense. Now, so that means the x component of 3 will be what? Very good. Negative what? Negative 10. Okay? East has to be equals to west. And then north has to be equals to south. So that will be negative 5. Very good. So F3 has two components, minus 10, minus 5. Newton. And then we are back to finding, vector using components. You need to find the magnitude. So maybe they ask you to find the magnitude, so you have to use Pythagorean theorem. And then you need to find the angle. So alpha will be tan arc tangent 5/10. We did that many times. Do you agree? So you need to, and then after that, you need to find that angle here. I don't know which color to use. This one. If you go from the positive x-axis, then you need to add 180 degrees. Are you with me? Right? Now, if you think it's too hard, it's fine, okay? It's don't have to do it this way. You can say x and y component. You can say f1, f2, f3, and the x component need to add to 0, and the y component needs to add to 0 when you add them up. That's a different way to do it. So the x component of f1 is 0, the y component is 5, the x component is 10, the x component is 0. That's my unknown. So you have 0 plus 10 plus x equals 0. Okay, so the sum of all the x components equals 0, the sum of the y component equals 0, and you will get the same thing. Agree? Okay, or you can do it this way. You can say f1 has two components. It has a 0 and a 5. f2 has two components. It has a 10 and a 0. f3 has two components, x and y. And you know that the net force has to be 0 and 0. So it means this plus this plus this equals 0, that plus that plus that equals 0. You can put a plus here and an equal there. Okay, so you have different ways to do it. Any question? Okay, so try to do this one. It comes from the book. This comes from the book or the homework. Mm, Okay, 1/4 is along this, so 60 here. The y-axis 75. Okay, so imagine it's a box on the floor. One student is pulling in this direction, the other one is pulling in that direction. So it's an equilibrium. So it's a mass. You have one string, and you need another string here. So what's going to be the x component? Very good. And the y component? Negative 75, you're right. Okay. You just have to be careful that when you find this angle here, you have to decide, is it this one or that one? Because they're going to be complementary, right? So that will be arc. Oh, we don't do it this way, tan. Someone is listening to music. 75 over 60. Is that right? And then you have to find this angle. Yes? Uh, is that right? The magnitude, we need to find the magnitude. We have to use Pythagorean theorem, right? This here, it's 75. And so that will be 60 here. It depends. You can use this one if you want. That will be 90 minus whatever you find. So in that case, you can use 60 over 75. 60 is this. This is 60 here. Yes or no? Now, if it's hard, you can say the sum of the x component equals 0, the sum of the y component equals 0, and you will get the same thing. Okay, so you see, I did it for you. You can use this way. This is the long way. X component, y component, y component. When you add them up equals 0. When you add them, oh, you saying that they ask for the magnitude. The magnitude is 96. 96. That's what you were saying. Okay, okay. I spaced out. Yes. So magnitude, we don't care about the direction. You're right. Okay, let's try to do this one. So this one you need it's this one. So this one you have two ways to do it. Yeah, you have the geometry way and the algebra way. So this is here 40 degrees and this is 40 degrees. And each, yes. And you can use a parallelogram. I'm going to use a parallelogram. So you have two ways to do it. Okay, you can use geometry or you can use so you have T1 and then you have T2. T1 and T2 are not equal to each other, but T1 equals T2 equals T. The magnitude is the same because the angle is the same. Okay, the direction is not the same, so you cannot say that T1 in vector is not the same as T2, but the magnitude, so these are the magnitude, yes, they are equal to each other. Magnitude are equal to each other because the angle is the same. So I'm going to call the magnitude T. Agree? So these two add up. You see, you have a beautiful parallelogram. That will be some souvenir from middle school. Okay, nice parallelogram here. So you need exactly the opposite here. That will be your weight. So it's a box. You have T1, T2.
That's 450, so it's 4,000.
Yeah, thank you. You're right. I was checking if you are paying attention. Shoot. You're right. 4,000 Newton, and this is 400 kilograms. Okay, so you have two ways to do it. You have two ways. So this is 40 degrees. If this is 40 degrees, that will be 40s. So you can do it geometrically, okay? Because you need to find this magnitude. Agree? And you see that magnitude is going to be twice. I'm going to do it the long way first, and then I will show you the shortcut. So if I do it the boring way, I mean, you have three ways to do it. I'm going to do it this way. Everything up has to be equals to everything down. Do you agree? What is pulling up? It will be the y component of the strain. Do you agree? Right? You have two, the tension has two components. X component, they are busy fighting against each other. And you have the Y component, they don't fight, they team up. Okay, they say, okay, yeah, I'm gonna help you and you're gonna help me. We're gonna be a team. We work together to lift those 4,000 Newton. So they team up. So you have the Y component of T1 plus the Y component of T2 teaming up to fight 4,000 Newton. So that will be T, because the tension is the same, cosine 40 plus T, always in magnitude, cosine 40 equals 4,000. So you have one apple plus one apple, that will be two apples. So if you do it this way, we don't care about negative, it's only the magnitude, okay? Or everything up equals everything down.
It's not two of these words.
Will be, are we good? 11:59. Okay, so that's gonna be, the answer will be A, very good. 256 Newton. So that's one way. The other way, if you do a little bit of trigonometry here, if you look in here, you see that plus this. You work in that triangle here. You work in that triangle here. It's a right angle triangle, and you see that cosine 40 equals, that's going to be half. So that will be 2,000. That will be 2,000 over hypotenuse T. Okay, you go even faster. You see, if you walk in that triangle here, if this is 4,000, this is 4,000, that's going to be 2,000. So in that right angle triangle, you can say cosine 40 equals adjacent over hypotenuse. That's way number two. That's a beautiful, elegant, it's a very elegant way. And now, if you want to do it the really boring way, so then you're gonna say the x component here is gonna be t cosine 60, and that's gonna be t sine 60, and that will be t cosine 90 plus 40, 130, and t sine 130, and it has to be equals to 0. So you choose your way. Yeah, you have 3 ways to do it. Question? No, if you want to do it the components way, do you remember when I told you that to find the component, you need to take the angle with the positive x-axis? So if this is 40, that will be 50, right? I made a mistake. That will be 50. F2, that will be 90 plus 40. Well, that will be 130, right? And you will get the same thing. Or you can do t sine 40 here. Sine 40 is the same thing as cosine 50. Any question, let me know. Is it open?